Welcome back to the next video, everybody. Today we're going to prove proposition 3. I think this is the third of 4 propositions we're going to need to prove the general case of R equals T, assuming the minimal case. Okay. First, we need to define some quantities. Keep all the notation from the previous videos. In particular, we have a nice representation rho bar with a bunch of cool properties like modularity and irreducibility, etc. And we're going to let sigma and sigma of rho bar, also a quantity defined over the previous couple of videos, be a finite set of primes. Let's let P be a prime in sigma of rho bar minus sigma, and we'll define the following quantities. If P isn't L, we'll define HP to be H1 of GP, acting on add 0 rho F tensor K mod O, divided by H1 of GP mod IP, acting on that same space. Okay, so it's just kind of it's like the quotient of the full cohomology group with the unramified classes, sort of. And then what happens if P is L? What is H sub L? It's H1S S of GL divided by H1 F of GL. So semi-simple classes divided by flat classes. Okay. For a prime P in sigma rho bar minus sigma, you can define CP in the Hecke algebra T sub sigma by P minus 1 times quantity T squared P minus P plus 1 squared. Okay. Now, we defined this set of new forms n sub sigma over the last couple of videos. So we're going to take a new form F there, and we're going to let it have Fourier coefficients in O so that its local numbering is just O. Projection to the F component then out of the Hecke algebra gives me an O algebra homomorphism, which I'll call pi from T sigma to O. And the push forward of the universal modular type sigma deformation by pi is, of course, just equivalent to rho F by essentially the defining properties of universal modular deformations. Okay, here's the key proposition. It's a crucial bound on cohomology. It tries to keep track of how big the type sigma cohomology groups grow as you increase the size of the finite set of primes involved. And we'll call this proposition 3. It says if sigma is in sigma prime is in sigma rho bar, then the cardinality of H1 sigma prime divided by the cardinality of H1 sigma is at most the cardinality of O mod pi of the product of the CPs where P runs through sigma prime minus sigma. So the primes sort of in the bigger set sigma prime, but not in the smaller set sigma, sort of determine the growth, all right? Moreover, if we have equality, then the following sequence must be exact. 0 to H1 sigma to H1 sigma prime to the direct sum of the HPs where P runs through sigma prime minus sigma to 0. Okay, so let's prove this. We'll let P be a prime in sigma rho bar minus sigma. Then, by definition, pi of CP is P minus 1 times quantity APF squared minus P plus 1 squared. And this has to be non-zero because P divides NF the level of F. And so the magnitude of APF is at most 2 root P by, this is proven in like Diamond and Sherman. It's also proven in the Diamond-Darmon-Taylor notes, Theorem 1.27, just for example. Okay. Next, if P is in sigma rho bar minus sigma and not equal to L, then by inflation restriction, which is a concept covered in chapter 4 of this playlist, you see that H1 of GP divided by H1 of GP mod IP is nothing but H1 of IP, although you have to put GP invariance on the space you're acting on, of course. Okay. But this action here is trivial. And so from chapter 4, again, we know that H1 when the action is trivial is just Hom, right? So this guy is actually just Hom GP IP add 0 rho F tensor K mod O. Okay, but now we got to get a handle on this guy. The point is the module we're acting on here is L infinity torsion. And so our morphism, any morphism here would have to factor through tame inertia, which we know, this is another number theory fact, tame inertia is really just, we'll call it S, and it's isomorphic to the product of Z sub Q over primes Q that are not equal to P. So it's the product of all kind of suitable copies of the Q-adic integers, okay? And then also morphisms here are morphisms of GP modules, right? So Frobenius has to act the same way on both sides of the morphism. But we know what Frobenius on tame inertia is. It's multiplication by P, again, a standard number theory fact. So if we let Fp be the subspace where Frobenius acts by multiplication by P, this quotient here, which is this, is now really just Hom SFP, okay? But what is Hom SFP? I claim it's Hom ZLFP, which is very obviously FP. Why the first isomorphism? Well, if you let S prime be S and you get rid of the L factor, then S prime is definitely compact. And since F is continuous, for suitable homomorphism F under discussion, then F of S prime is compact. So it's got to be, in this case, that means it's got to be killed by a sufficiently high power of L. But that means 0 is like L to the n F of S prime for some large enough capital N. And since F is a homomorphism, you can move the L to the n inside and you get F of L to the n S prime. But L is invertible away from the L factor of tame inertia. And we got rid of the L factor from S to produce S prime. So this here is really just F of S prime. And so F of S prime is 0. Okay. And so that gives you this isomorphism. So the question then is, what is FP? Well, FP by definition is just H0 GP, add 0 F tensor K mod O's kind of -1 Tate twist. In fact, just by definition. I'll say a little more though. In general, if M is a GP module of characteristics, say L, then M-1 is just the same module, but Frobenius at Px by its original action times 1 over P. And so what is H0 M-1, which is kind of what we're looking at here? It's the set of all x and m such that 1 over P times Frobenius of P of x is just x. But that's just the space of all x such that Frob P of x is Px, but that's just what FP is, right? Okay. All right, so here's our quotient. We have to keep it's like proof by rewording a million times. Okay. Now, what is this space? It is literally, by definition, the kernel of 1 minus Frobenius inverse at P on add 0 rho F-1 tensor K mod O. And so now there's a general fact. What do we want? We want the O length of this, right? But the O length is just the valuation of the determinant. More generally, if M is a free O module of finite type and F is an endomorphism of M with non-zero determinant, then the kernel of F acting on M tensor K mod O is finite with length evaluation of the determinant. Indeed, if you take X to be a uniformizer and U to be an endomorphism of M, let's say, then for large N, you have an exact sequence like this: 0 to what we'll call Kn to M mod X to the N, M mod X to the N via our map U to what we'll call Cn to 0. What is this Kn here? It's the X to the N torsion of the kernel of U as an endomorphism of M tensored up to K mod O. And so the full kernel then of U is the union of these Kns. But M mod X to the N is finite, and Kn has the same length as that of Cn by general properties of exact sequences. And the result then follows from linear algebra. And I will discuss what I mean by that in the next video. I don't want to get too far into the weeds here. Okay. So really, we need the valuation of the determinant of this guy. Okay. But the point is, this is just now a calculation, right? You know the characteristic polynomial of Frobenius at P of rho F. It's just x squared minus APFX plus P. And so you can just calculate the valuation of 1 minus Frob P inverse. And lo and behold, you get pi of CP. Okay, so our quotient then has to be the valuation of pi of CP. But that's just by definition the length of O mod pi of CP, which is exactly what the proposition is claiming, right? Okay. Now that only works when P is in L. What if we're at L here? I won't say too much about this. If L happens to be in sigma rho bar minus sigma, then proposition 1 of this chapter and basic properties of Galois representations attached to new forms, you can see DDT theorem 3.1f, for example, show immediately, and this is an immediate calculation, you get the cardinality of H1SS divided by the cardinality of H1F, which is the quotient whose size we want to estimate, actually equals the cardinality of O mod pi CL. And then the result follows by considering video 11.6. Okay, the full result of the entire proposition 3 follows by considering 11.6, and I'll let you go visit that. Okay, so there you go. There's another proposition out of the way. So we're going to get into the biggest of all the propositions that we'll need, proposition 4, starting next video. And this is going to be a very, very hard theorem comparing the sizes of the congruence modules as sigma increases to sigma prime. So I'll see you all then, and thanks for watching.